I'm now happy to invite our first keynote speaker, Dr. Robert Haley, who will educate us on the science of climate change. Dr. Haley is an internist. He's a distinguished teaching professor. He attends on the Parkland Hospital Internal Medicine Teaching Service and teaches medical students, research faculty, and graduate students in the SMU-UT Southwestern Joint Graduate Program. He served for 10 years at the CDC. He received the U.S. Public Health Service Commendation Medal, and he also founded the Division of Epidemiology at UT Southwestern. For the past 16 years, he has studied the health effects of air pollution in Dallas from nearby coal-fired power plants. He lectures widely on the scientific evidence for climate change. This year, he serves on Dallas County's Public Health Advisory Committee, developing COVID-19 response policies for the county government. He advises performing arts organizations, the Dallas Federal Reserve Bank, and SMU. And he has many honors. These include the Dallas Historical Society's Award of Excellence in Community Service, the Health Sciences and Medicine, the University of Texas Regents Outstanding Teaching Award, the Texas Medical Association's Lifetime Achievement Award for Outstanding Contributions to Medicine through Public Health. He is also the holder of the U.S. Armed Forces Veterans Distinguished Chair in Medical Research, honoring America's Gulf War veterans. Dr. Haley, we're thrilled to invite you now to present. You can now share your presentation slides. At the end of his presentation, we will open to questions from the audience, and we encourage you to submit any questions you have using the Q&A feature below.
Well, thank you very much, Alice, for you all inviting me to speak here today. I've been giving this talk all around the country for a good while, a number of years now, and it's the more I give it and the more I study this, just the more important this obviously is becoming to me. So let me share my screen here now to show my slides. Okay, and make it a little bigger. Okay, can you see that all right?
That looks perfect, and we can hear you perfectly as well.
Okay, wonderful, good. All right, I'm going to kick off our conference here, and I think in the best way. We're going to start off talking about just the scientific evidence on climate change, and then a little bit at the end on the ethics of skepticism versus denialism. But, you know, as we study the next couple of days, the effects on health and healthcare and so forth, it's important to start off, though, with understanding what the evidence is about this problem. You know, if you don't know the evidence, it's very hard to really evaluate what it's going to do, what the problem is going to do. And it's really hard to defend this against people who are not convinced. And so we're going to start off with the evidence, the scientific evidence. And I have a handout that either you have or you will be able to get. Did we already send this out, do you know? Or are we?
The handout will be sent following your presentation.
Oh, good. Okay, so we'll send out the handout as a souvenir of the talk, and it follows the talk very carefully, but in words, and the main slides that I'll show are embedded in it. So you can, you know, as you go through this, it's a lot of complex information. Hopefully, I'll make it very easily understood to you. But having the handout and then going back and being able to read it and study it just the way you would a lecture in medical school or nursing school or whatever, I think this will be very helpful and give you a great background for understanding this problem going into the future. Okay, so first of all, I have no conflicts of interest to describe or off-label use of drugs, so I should be very unbiased. Except to say that to remind you of some of the dramatic effects we've obviously been seeing, the fires in the western United States. Here's the smoke plume last summer that went all over the country, from the fires in the Northwest all the way up into the Northeast and the Midwest and so forth. And then last year, 2020, was only the second time in history we had 5 major hurricanes in the Atlantic at the same time, a very rare occurrence. Now here's your reading list, all right? If you want to go into this in great detail, I would suggest these, and these will be in your handout. First of all, go to the NASA website, nasa.gov climate.nasa.gov. Very easy to remember, climate.nasa.gov. You know, NASA was the first agency really to look into this and to discover it and present it to Congress, and they've led the way all along for the problem and control of it. There's a very good book by Michael Mann, who's a major researcher in this area at Penn, called Dire Predictions, Understanding Climate Change, the Visual Guide to the Findings. It's in a second edition. It's actually a picture book. It presents a lot of what I'm going to present today and more, but in pictures and diagrams and tables and so forth. So it's very easy to understand. So those are terrific sources. Spend a lot of time going through the NASA website. And then if you really want to get into the heavy data, the Intergovernmental Panel on Climate Changes, a couple of thousand scientists who provide their time to study this and put together, and they put together a report every 4 or 5 years. And the last 3 of these, particularly the 6th assessment report that just came out last year, the physical science basis, these are really difficult reading, but they're very rewarding if you can do it. All right. So now, how did I get into this? Well, first of all, let me say I'm a professor at the medical school in Dallas, and we have a common table where a lot of the faculty eat lunch. And I had an experience that I was discussing with my colleagues. Let me tell you the experience, and I'll tell you about those discussions. This is a scientific paper we published in 2013 in JAMA. It was the 2012 West Nile encephalitis epidemic in Dallas, Texas, the largest epidemic of West Nile in the country, in history. There had been, West Nile had been introduced into Texas in 2002, and it percolated along a little bit with a few cases of West Nile neuroinvasive disease, that is encephalitis, brain infection with the virus. It's mosquito-borne. And then in 2006, we thought we had a big epidemic. We had 67 cases of encephalitis and several deaths. And then it kind of looked like it was disappearing. And then suddenly in 2012, we had the mother of all West Nile epidemics, 173 cases of brain infection, 21 deaths. It was a calamity. Right in the middle of the city. It was the center point. So turns out we had more data than anyone ever had in a West Nile epidemic. And so we took it on and began studying this epidemiologically. And we looked at a number of predictors of what predicts whether you're going to have a small or large number of cases in a given year. And it looked like the major predictor was the number of hard freeze days, number of days where the temperature goes below 28 degrees in December through March during the winter. And here's the very few freeze days, a very warm winter, and up here is a very cold winter with lots of freeze days. Here's the year of the epidemic, of the number of cases. So look here, 2012, the year of the big epidemic, had the fewest freeze days ever. In 2006, the next epidemic was here, 2006, all right, and then a bunch of these in the middle, and then 10 and 11, which had almost no cases, were the warmest, the coldest years. So here are the warmest, the fewest freeze days. Well, this is important because mosquitoes that are infected with West Nile through the summer, if over the next winter, if it's not very cold, many of them will survive and be able to infect other mosquitoes and people and birds early in the spring, and you have an early epidemic of West Nile among birds, which then has a time to grow and spill over into humans before the mosquito biting season ends in late July, okay? Whereas if they're all killed in the wintertime, then it takes a long time for the virus to grow up, and it doesn't get going enough to cause an epidemic until it's too late and mosquitoes stop biting. So you see, that means that the the warmer the winters we're going to have, the more of this we're going to have in the future because it's not going away. And that hit me, wow, you know, that climate change is coming. This is going to become more common. And so sure enough, there was literature on that. People were already speculating on that this is going to become a bigger and bigger problem. All those arboviruses transmitted by mosquitoes will become more common. Well, so I thought if I want to study this and be a good epidemiologist, I need to understand climate change. So this started my very intense study of the problem of climate change. As I was doing that, then I would have lunch discussions with my colleagues, and I would ask them, and they all had a strong opinion about climate change, being a pretty strong bunch. But I would ask them, and it turned out none of them had the slightest idea what the evidence was for their position, whether they thought it was going to be a problem or climate change wasn't going to be a problem. They had no idea what the evidence was. And I thought in a real evidence-based group like that, a medical school faculty, that was really unusual. And so that's what gave birth to this talk. I decided then, as I did my study, that I would develop a talk to doctors and explain to them the evidence, because I find that when they understand the evidence, they become much more concerned about the problem and much more ready to go out and advocate and try to fix the problem. Okay, so that's what we're going to do today. I'm going to tell you what I've learned over the years about climate change and what the evidence is for it. All right, now the first thing you got to realize, this hit me one day as I was studying it, the question about climate change is not one question. And if you treat it as one question, you'll always be confused. It's actually 4 questions. And if you distinguish these 4 questions and take them one at a time, everything becomes real easy and understandable. And so that's what we're going to do. So the questions are, first, is the Earth's surface temperature warming? Okay, that's a straightforward empirical question which data can decide it. Is the warming due to human effects or natural phenomena? Again, a very objective question with an objective data-related answer. But we get into trouble when we get to the third one. Is the warming climate a serious threat to humans? Well, now, so what's serious? The word serious calls for a value judgment. What's serious to one person may not be serious to other people, or you might be able to sort of deny that that's serious. Okay, so this one not only is evidence, but also a value judgment. And finally, should society invest in curtailing climate warming? And whenever you talk about investing in a problem, in solving a problem, you're going to take resources, in this case, a lot of resources, and move them from one area into this area. Well, that means there are going to be winners and losers. And whenever there are losers, you can bet those people are going to fight you. And they're going to deny what you're saying. And mainly, they're going to try to confuse everybody so that people aren't sure. And what happens is then they blur these 4 questions because they're so upset about losing. And they make everybody think that the first 2 questions are blurred and are value judgments, when in fact they're not. Okay, so let's go through these and see what you think at the end. The first question is the Earth's surface temperature warming. All right. Well, here are the results of 10 studies. And these studies have looked back 1,000 years and actually now 2,000 years by looking at proxy measures, ice cores. They drill down in glaciers and ice sheets, and they get ice cores, and they can look at each level, and they can actually analyze the little air bubbles that have been trapped in there and measure how much carbon dioxide is in the atmosphere. And they can look at number of pollen grains and so forth, and figure out what the average temperature was, and so forth, and drill down into mud sediments down the bottoms of lakes and do the same thing. Look at tree rings and so forth. And so you get different studies based on different types of proxy measurements. And of course, we've been measuring it for the last 100 some odd years directly. Turns out, if you look at this, there's some variation, some difference among the studies, But notice that they all show a slow cooling trend from the last 2,000 years, okay? And then suddenly, at the advent of the Industrial Revolution in the mid-19th century, suddenly a leveling off and then a dramatic upshoot. Look, a geometrically increasing increase in the global temperature. Here in the last 2,000 years, the slow cooling trend. Here is since the Industrial Revolution. You see it sort of leveled off here, stopped going down, and then it started going up slowly. And then in the 1980s, it suddenly turned up really fast. And this was when the developing countries like China and India and others sort of joined the Industrial Revolution that had been going on in the United States and in Europe. Okay, and so now you see, in fact, it's even looks to be in the last several years turning up even more steeply. Okay, so the evidence is pretty clear that it's warming. Now, if that's true, you would expect other things to be happening. And so here are those other things. Well, here's the surface land surface temperature, and the same thing since the 1850s. That same thing, just not as steep a scale here on the left. Okay, increase in temperature. Here's sea level. The sea level is slightly increasing. It's just centimeters now. In a few centimeters, it's increasing. But here is the amount of heat dissolved in the ocean. Because, you know, when the atmosphere heats, a lot of that heat then sinks down into the ocean and warms the ocean. And it turns out this sea level rise up to now is almost entirely just due to the expansion of the water because it's being heated. Interesting. It's not due to melting ice sheets, dumping water into the oceans and raising the sea level. That hasn't really happened to a great deal yet, but it's going to. And what we're seeing now is just a heating effect. All right. Here's the specific humidity. You may know that the humidity has been increasing. I was in college in the 1960s. Boy, that's a long time ago. And it was, when I grew up in Dallas here, it was not very humid. And now the summers are really humid. And I'm not dreaming. That's really happening. Okay. Because, you know, warmer air contains more water. When you get into pulmonary disease physiology, you'll learn that we blow warm air down people's airways because it holds more water and it doesn't dry out. It keeps their membranes moist. So as the atmosphere heats, it contains more water and that more humidity. Here's the amount of snow cover over the earth measured by satellites. See, it's been downtrending. All right, here's the amount of sea ice floating all over the northern and southern parts of the ocean. It's declining. Here's the change in the glacier mass, where glaciers are all getting smaller and melting. Okay, and you know, glaciers are the major source of water for about 80% of the world's population. So here, it's clear that the things that and there are many more, but these are the main indicators, but there are a lot more, but they're all happening. So it's clear from many different perspectives that's happening. Now, I mentioned the ice sheets. This is really important. There are only three ice sheets in the world: the Arctic, the North Pole, okay, Greenland, and Antarctica. Okay. Now, the major ice sheet on the North Pole, the Arctic, is floating. There's no land up there. It's not a land mass. It's just an big ice sheet floating in the water. So if that were to melt, it would not increase the level of the sea. You know, like when you got your iced tea there at the lunch table, if the ice in your glass melts, the water doesn't overflow because it's already in the water, you see. But if you add ice cubes, you know, or pour water, it'll overflow. So that would happen if the Greenland sheet melts, for example. And here is the Antarctic. The major one is the Antarctic ice sheet. Here, there's the eastern ice sheet, which is the really big one. Okay, and then this is miles thick of ice, and this is the western Antarctic ice sheet, which is thinner and smaller. and it's already starting to disintegrate, as you can see the red parts. Now, Antarctica contains 75% of the world's fresh water is frozen here. 75% of the Earth's fresh water. That is a lot of water. So if these three things were to go, we would see a major increase in the levels of sea level. Okay, we'll talk about that later. Now, another really important basic fact is that climate warming is not uniform over the surface of the Earth. The land areas are warming faster than the oceans. Okay, here, the lighter areas are warming less and the darker areas are warming more. See, the land areas less than the oceans, and the northern hemisphere warming more than the southern hemisphere. That's because the sun is tilted, the Earth is tilted toward the sun, so the northern part of the world is pointing more toward the sun, gets more energy from the sun. And what's really scary, though, is that the very northern Arctic region is warming faster than any of them. Okay, and it's warming 3 to 4 times faster than the average. So we have already, the Earth overall has warmed about 1.1 degrees Celsius since the Industrial Revolution. The Arctic has warmed already 3 degrees and is starting to have summers in the 80s, which never happened before, okay? So remember this, because this is going to explain a lot of what we're going to see as we go. Now, here's just the month by month temperature curve, average temperature of the world month by month. And notice, here's back at the Industrial Revolution, and here the pink and the orange as we get closer to now. And so you see, it's just every year, every month is getting warmer. So this is not some unusual event that's happening at some time of the year. This is the entire year's getting warmer. That's also an important fact. So is the Earth's surface temperature increasing? Question one. The answer is undoubtedly yes. There's no question about that. Nobody who knows the evidence doubts that at all. Okay. Question two, is the warming due to influences, human influences, so-called anthropogenic, anthro meaning human, genic meaning cause, so anthropogenic or human influences, or natural phenomena? Is this just the sun getting hotter and warming the Earth more, whatever? Well, in order to understand that, you need to understand the greenhouse effect. So here is a little cartoon illustrating it. Okay, the Earth is warmed by the sun. The energy is pumped into the Earth by the sun's light rays. When they come down, sun can be reflected back into space by clouds, soot, volcanic soot. That's when a volcano erupts, it can reflect a lot of that. The soot put in the air by the volcano can go all around the world and reflect the sun, a lot of the sun's rays back, and could even produce a very dangerous, like a nuclear winter, and that has happened actually in the early 19th century. Anyway, when it hits the ground, it's absorbed and warms the ground. And interestingly, the white areas covered by ice reflect a lot of that energy back out into space. They absorb less, whereas the dark colored land surface, land or tree covered, absorbs more because it's darker in color. Well, that's important because if we melt the ice, we're going to expose more dark colored water, which will absorb more. We will accelerate warming, which will then melt more ice. So you get a positive feedback cycle there. It's called the albedo effect. Anyway, then it turns out then there are in the upper part of the troposphere, there can be the accumulation of these greenhouse gases, carbon dioxide, methane. Methane may be the biggest problem. Nitrous oxide, ozone, ground level ozone, chlorofluorocarbons and hydrofluorocarbons. These are refrigerants that you use in your air conditioner and so forth. And water. Actually, water vapor is a greenhouse gas, like in clouds. And what these do, these gases absorb, well, there's one other fact. Let me tell you how these work. So in the daytime, the sun warms the surface, okay? It gets warmer. At night, when the sun's not shining anymore, the heat that's in been absorbed during the day, some of it will radiate back out into space as infrared radiation. All right, now remember, infrared radiation is like if you're warming yourself in front of a fire, you're not actually feeling the flames touching you. Of course, that would burn, but you're standing back, but you're still getting warm, and that's because of infrared radiation coming out and warming you. This form of light, but it's coming from the fire and warming you. So some of that warmth can go back out into space, just like the fire is warming you. It radiates out into space. Whereas these greenhouse gases can capture some of it, absorb it, and reflect it back down to the surface. So they act as a blanket, trapping a lot of this that used to go out into space, trapping it and keeping it in. So it's like a blanket. And that's the greenhouse effect. And as this builds up, it more gradually warms the earth more and more and more. Now, this is nothing new. This was described, you may remember the name Joseph Fourier, first described the greenhouse effect in 1824. John Tyndall, the Tyndall effect, you heard of probably, measured radiative properties of different gases like CO2 and methane and all of those. But the credit for really defining the greenhouse effect goes generally to Svante Arrhenius. He's a Swedish scientist who in 1896 published a paper that, several papers, reducing the greenhouse effect to a very simple equation of physics. So he said, this is a matter of physics. It's not something very complicated. That is, the change in the temperature over time is a function of the log of the change in the amount of carbon in the atmosphere. So from the original carbon level to the new carbon level, okay, that actually directly determines the change in the temperature, and there's nothing else complicated about it. So it's a matter of physics. As carbon in the atmosphere increases, the temperature is going to go up, period. Okay, and he said, he predicted that the industrial carbon dioxide emissions from industry in the earth was sufficient to cause some global warming, but he said industry could never release enough CO2 to really matter. And that's where he was wrong. He got everything else right, but that was incorrect. And he pointed out, due to the equation, that doubling of the CO2 level in the atmosphere would increase temperatures by 5 degrees Celsius or 9 degrees Fahrenheit. Now that's the average over the world. Now, to many people, that sounds like, oh, that's not very much, just 5 degrees. I could take that. It would be a little hotter in the summer. Wait a minute. This is very different from what it's going to feel like. Okay, it'll feel uncomfortable, but it's like if you have a patient whose normal temperature suddenly increased by 5 degrees Celsius or 9 degrees Fahrenheit, went from 98 to 100 and 106 or 107. Yeah, that's not very many degrees, is it? But that's enough to kill the patient, basically. It produce so many other effects that it would kill them. And that's why 5 degrees is just disastrous. This would end all of mankind and probably be a massive extinction of everything except the insects that would be left. Okay, so he was the first Swedish scientist to receive the Nobel Prize in 1903. All right, now let's see, how much CO2 is accumulating? Well, here's from the Industrial Revolution and before, for millions of years, it had not been over 300, and most of the time it had not been over 290 parts per million. This is the CO2 concentration in the atmosphere. Remember that, 300 or 290 or 300 parts per million in the atmosphere of CO2. However, by proxy measurements, analyzing those bubbles, in the core samples from the glaciers and so forth, they've estimated that here's the growth after the Industrial Revolution. Then since the late 50s, we've been directly measuring it on the Mauna Loa volcano on that island, the big island in Hawaii. And I'll talk about that in a second. But here's the curve of the amount of CO2 in the atmosphere. Notice that looks very much like the curve of the increase in temperature, okay, which is right here. See, these curves are basically the same. Here is the number of millions of metric tons of carbon emissions since the industrial age. I've pretty much aligned these graphs so they should be pretty parallel. And here's the amount of carbon put into the atmosphere by coal burning, by burning oil, burning natural gas, and producing cement. Actually, the chemical process in curing of cement releases CO2. It's interesting. Okay, we have been increasing 35 gigatons per year total. Now notice this curve looks very much like this curve, doesn't it? Those are superimposable. Now that doesn't prove that this causes this, but it's very suspicious. Now look at this graph. Here is for the last 1,000 years, the total CO2 emissions on the Earth, which was close to, very low compared to what it is now. And then suddenly after the Industrial Revolution, it's done like this, okay? Now here's the amount that's in the atmosphere, same thing, all right? Now, since the Industrial Revolution, humans have put 1,000 gigatons of CO2 into the atmosphere. That's 1/6 of the world's carbon resource. 1/6 of the carbon that's down there has already been mined and released into the atmosphere. Now, what is a gigaton? A gigaton is 1 billion tons of carbon. So we've released 1,000 billion or 1 trillion tons of carbon into the atmosphere. That is a lot. Now, 46% of it remains in the atmosphere, which is really bad. 30% has been dissolved in the oceans, and we're kind of lucky because that has acted as a carbon sink to take a lot of it, some of it out of the air. So this doesn't get quite so high. Now, on the other hand, dissolving it in the ocean has its own bad effects, because when you put CO2 into water, you remember in high school chemistry, CO2 plus H2O, what does it give you? Carbonic acid, H2CO3. And what that does, that slowly acidifying the ocean. Well, all the species in the ocean have never been acidified like this before. They've all evolved to, at least in the last 100 million years, they've evolved to live in an ocean of constant pH. And now we're reducing the pH, making it more acidic. So that's really bad. And if continuing, would eventually sterilize the ocean of all the species that we know. And, most of the world's population lives on bounty from the ocean. Okay. Now here is the big island of Hawaii and the Mauna Loa volcano up here, but what they have a field station here that measures air coming off the vast Pacific Ocean. So it's not contaminated by human sources as it comes right off. So it's the purest air on Earth. That's why they do it there. Just as orientation, this is the pie chart of the composition of the atmosphere. It's 78% nitrogen, remember 21% oxygen. And then these are the rare gases. Carbon dioxide is only 0.04% or 410 parts per million, somewhere around there, okay? And although it's a very tiny fraction, and this increase isn't going to take all our oxygen away, but it's very tiny because it's important though, because it's so active in trapping greenhouse gases, as a greenhouse gas, trapping heat and radiating it back down. That's why it's important. All right, now here's those same pictures. Here are some numbers now. Look, I want you to remember really quickly. You can remember these. In the last 35 million years, okay, the CO2 concentration of the atmosphere has never been above 500 parts per million. 35 million years, not above 500. Pre-industrial, it was 280 for many millions of years, and up to 300 maximum, just a couple of times. And as of July of this year, it's highest in the summertime. So in July, this last July, it was 416 parts per billion. Okay, so 280 or 300, we're at 416, and 500 is the maximum it's been in 35 million years. Think about that. What are we doing? Okay, so do you believe that this is caused, do you think this is due to what mankind has done? Okay, well, here's the evidence. Methane is, oh, I'm sorry, wait a minute, I'm getting ahead of myself. Yeah, I wanted to first tell you about methane because people are talking mostly about CO2, but methane, CH4, is actually emerging right now in this field. People are starting to think, you know, in the short term, we probably need to control methane more vigorously than CO2. This is the longer term goal. But this turns out to be really important. What is methane? Methane is natural gas. Okay, human emissions of burning things, the human emissions of methane are from natural gas production. Basically leakage from gas wells and pipelines. You may have seen in the news, the last administration eliminated all the controls on leakage of methane. It said, go leak away, you know, and now current administration is tightening that up and trying to take vigorous methods to, and there's even a new technology, satellite technology, tremendous technology that's starting to, with satellites, detect where methane is leaking out of oil wells and either abandoned oil wells and so forth, where they can go in and enforce cleanup and plug those wells to stop this leakage. The natural emissions, this is human emissions, but natural emissions are from anaerobic decompensation of plant matter. So when plants die and rot, the decomposition produces primarily methane. Rice production produces methane just in the production of it. Livestock belching and feedlots are just oozing out methane. And of course, volcanoes can produce methane among other gases. Here's the problem. Methane, and the opportunity as well, methane remains in the atmosphere once it's released. It remains there for only 10 to 20 years, whereas CO2 remains for centuries. So the CO2 we put up since the Industrial Revolution, that's going to remain there for the duration, okay? Whereas the methane will degenerate after 10 to 20 years. So therefore, if we could stop methane release, 10 to 20 years now, we would see a great cooling effect, a bonanza that would give us more time to control CO2. So this is really becoming a big issue. I don't emphasize it enough in this lecture because this is all sort of new thinking in terms of growing as a consensus now. Now, the global warming potential over 20 years, over the 20 years of life of methane, it's 86 times greater than for CO2. So the warming potential, trapping those heat leaving the earth, that effect is 86 times greater for methane than for CO2. So that's why it has a disproportionate effect. And since it goes away in 10 to 20 years, controlling that now should be the biggest priority, this in long term. Both of them we need to do. All right, now this is the graph. I want you to really look at this one. This is the one that just really captured my imagination when I first started. This is on the NASA website. Has been for a long time. All right, here is the CO2 concentration of the atmosphere in parts per million. All right, here's 300. Hasn't been above this in hundreds of thousands, several million years. Here's 280, where it usually is the maximum. Notice that see, this is 600 or 400,000 years right here. Notice how the CO2 concentration fluctuates over hundreds of thousands of years, and there's a cyclical effect. It goes down and up and down and up and down and up and down and up. See that? And when you get to the bottom of this, or 50,000 years or so, that is a glacial period. that is an ice age. And there have been recurrent ice ages through the eons. Look at that. And in between, when you get these sudden rushes of CO2 into the atmosphere, look at this, sudden release of CO2 into the atmosphere, you then get a temperate zone for 20,000 years or so, okay? And it varies in amount of time. That's a temperate zone where the temperature is warmer, okay, before you degenerate then down into another ice age. Isn't that interesting? Did you ever know that? I didn't know this before I started studying it. Now, the end of the last ice age was about 11,000 years ago, and there was a big jump. And then look here, this little bit of downtrending. This was in the 18th, actually from the last several thousand years since the end of the last ice age, it was starting to go down again, just like this. See, it was probably going to bounce around a little bit. It was going down. Remember that I showed you for the last 2,000 years, there's been a cooling trend? Well, this is it. And then the Industrial Revolution happened, and then boom, and now since the 1980s, boom, look at that. We're now at 416 parts per million. Okay. Well, we've not been up here since for millions of years. To 400, almost 35 million years. And notice, where did this carbon come from? This is not carbon that was released like this. This probably came from suddenly the beginning of a positive feedback cycle that melted a lot of the CO2 and methane that was frozen on the ocean floor. It sort of suddenly started some positive feedback loop, a vicious cycle that suddenly released it all within 1,000 years or so, very quickly. Well, that hasn't happened yet. This is all from burning fossil fuels, and I'll give you the evidence for that in a little bit. So this has not happened. What happens if this happens? Okay. Well, you see, this is more complicated and more dire than most people realize. This isn't just a few infectious diseases and some asthma. This is the end of mankind. All right. So is the buildup of CO2 coming from natural causes or anthropogenic human emissions? Well, I've given you the evidence it's human. Let me talk about natural. Okay. Since 2000, okay, well, first of all, is it the sun getting hotter? And this is some of the deniers were making a case, oh, the sun's getting hotter. That's all it is. Well, here is actually the radiance of the sun, the heat coming from the sun. This is measured. It fluctuates, during from summer to winter and so forth. But then here's the average. And notice at the time when the temperature of the Earth was dramatically increasing, the sun's heat was actually declining slightly. So clearly the sun, the amount of heat from the sun is irrelevant, is not causing this. Now this is fascinating information now. Here's the greenhouse diagram I showed you before. Here is a graph since the 1880s, since the Industrial Revolution. In red is the measured increase in global temperature. Notice these temporary drops. This is from the eruption of a major volcano, putting ash, and dust up in the atmosphere and reflecting the sun's rays back. But that only lasts for several years. You see there? Okay. So here's what actually happened. The blue line is from the supercomputer models saying if humans had not been putting all this CO2 and methane and other gases into the atmosphere, here's what it would have been. Okay, here are the volcanic effects and so forth. Here's what it would have been. And notice, this is what we know. And so that suggests that it's human caused, since this is all takes into account all the natural causes of putting carbon in the atmosphere. So, but the fascinating thing is this has been measured not only here, but it's been measured in the troposphere where we live, that is down near the Earth. It's also been measured up in the stratosphere by various technologies, such as satellites and planes flying up and measuring it, measuring the temperature and so forth. And while this has been warming, the measured temperature of the stratosphere has been cooling. Now think about that. Down here, it's been warming, continues to warm. In the stratosphere, it's been cooling and continues to cool at about the same rate that it's warming down below. Now, if the sun was getting hotter, what would happen? This would be getting hotter and maybe even hotter at a faster rate than down on the Earth. In fact, it's the opposite, which strongly supports the greenhouse effect and these greenhouse gases building up. If that's not enough for you, here's another experiment. And by the way, at the bottom here, I'm giving you the references so you go read these studies if you want. They're all published in very, very good journals, good science, peer-reviewed, and so forth. Okay, here's a study where they actually, remember how at night the greenhouse gases reflect the energy back down to Earth? This is a study of what is the energy coming back at night. And here's a spectroscopic breakdown of the wavelengths of energy being reflected back at night. And look, they happen to be just in those parts of the spectrum that are reflected back, known to be reflected back by carbon dioxide, chlorofluorocarbons, ozone, nitrous oxide, and methane, the greenhouse gases. So the energy that's being reflected back at night is the energy reflected back by the greenhouse gases, not other energy. Now, what about what's escaping into the upper atmosphere at night? This is a 26-year study where they measured the spectrum, the wavelength of energy coming back out at night up into the upper atmosphere. And from over 26 years, there's been a decrease in the amount of energy coming back at night. And the parts of the spectrum where the increase is the most is the parts that are blocked by greenhouse gases, CO2, chlorofluorocarbons, carbon dioxide, ozone, chlorofluor, and methane. So what's being reflected back is that reflected by greenhouse gases, and that's no longer escaping. The decrease in energy escaping at night is just those parts of the spectrum that are blocked by greenhouse gases. So this is very strong argument of experimental evidence. There's been an experiment done to show that, showing that it connects the global warming with the greenhouse gases. Now, so where does that carbon come from? What carbon is that that's building up in the atmosphere? The CO2 and the methane, the carbon up there. What kind of carbon is it? Where did it come from? Maybe it came from just the dying of plants over the years. Maybe more plants are dying now, or maybe more more cows are belching and so forth. Is it natural coming out recently? Okay. Well, here's a fascinating experiment. Okay, they measured. Okay, and here you have the same curve I've been showing you. This is the CO2 concentration of the atmosphere, all right, in parts per million, all right, measured on the Mauna Loa volcano and at the South Pole. The blue measures are at the South Pole, the red measures are at Hawaii, okay? Now here is the concentration of oxygen in the atmosphere, also measured in 2 places. Notice that while CO2 is increasing, oxygen is decreasing. Now, the amount of decrease is infinitesimal. It's not going to rob of oxygen, but there is a measurable decrease in the oxygen concentration of the atmosphere. And notice that the slope of this is twice, though inverse, twice the slope of this. See, this is kind of not very steep, and this is twice as steep, although going in the opposite direction. See that? So by a factor of 2, it's exactly twice the slope. Now, why would that be? So as one molecule of CO2 is produced, 2 atoms of oxygen are disappearing. Well, remember in high school chemistry, when you burn something, you burn carbon, you have 1 atom of carbon joining with 2 atoms of oxygen, releasing heat, which is burning and a flame and so forth. And that produces 1 molecule of CO2. So for every molecule of CO2 that appears, 2 atoms of oxygen disappear. And that's exactly what has been measured. So that suggests that the CO2 that's up there is actually from burning of carbon, not from natural formation in the rotting of plants and so forth recently. Okay, so that suggests that this is burning of, actually combustion, burning of carbon. Okay, now what carbon is that that's burning? Is it bonfires and, you know, fires that we have in our fireplace from, you know, we go chop down trees and burn them? Is it forest fires? Okay, or is it fossil fuels burning? Well, this is called the atomic fingerprint, or the atomic proof. Okay, you know, carbon in the world is in several different isotopes. You have relevance here is carbon-12 and carbon-13. Carbon-12 has 6 protons, 6 neutrons. Carbon-13, 6 protons, 7 neutrons. You remember that? Well, it turns out that hundreds of millions of years ago, chlorophyll was more primitive than it is today, and the primitive chlorophyll primarily captured carbon-12 and put it into plants. You know, grew plants. Chlorophyll is the energy source for plants to grow. So it would incorporate carbon-12 into the plants. Whereas in modern days, chlorophyll is now evolved and it now incorporates more carbon-13. So you can differentiate carbon that was burned, that was laid down hundreds of millions of years ago and recently burned, from carbon that has been produced more recently and burned. So you look at the carbon-13 to carbon-12 ratio in the atmosphere, and here is the carbon-13 to carbon ratio, carbon-13 to 12 ratio. Here is the concentration of CO2 in the atmosphere, and as that has gone up over the last 2,000 years, the ratio of carbon-13 to carbon-12 has gone down as a mirror image. What that means is we are pumping more carbon-12 into the atmosphere. So the carbon-13 to carbon-12 ratio is going down because we're pumping more into more of the denominator, you know. And so the ratio's going down and more of that's going into the atmosphere. So the carbon-13 to carbon-12 ratio in the atmosphere is declining at exactly the mirror image of how much CO2 is appearing. So this proves that the carbon that is being pumped into the atmosphere was made into plants hundreds of millions of years ago. Well, what is that? That's coal and oil and natural gas. So together, these prove that the carbon that is increasing in the atmosphere and causing climate change is from the burning of fossil fuels, period. So, evidence implicating fossil fuel burning, the theoretical explanation of the greenhouse effect. Atmospheric CO2 levels are tracking CO2 emissions. Oscillating CO2 levels for 4.5 million years now are exceeded. Solar irradiance not increasing. Tropospheric warming with stratospheric cooling. Reflected infrared energy in spectrum of greenhouse gases. Oxygen disappearing at twice the rate CO2 is appearing, and the atomic proof, the decline of the carbon-13, carbon-12 ratio in the air. That's awfully convincing. So, question 2, is the warming due to human effects or natural phenomena? By conclusion, the scientific evidence clearly shows that the warming is largely due to human emissions of greenhouse gases, primarily CO2 from burning fossil fuels. And I don't think that anybody can refute that. That's not a question. So question 3, is the warming climate a serious threat to humans? Now remember, this now gets into a value judgment. Well, the average global temperature now currently is warmed 1.16 degrees. When I started giving this talk, it had increased by 0.9 degrees Celsius and 2.1 degrees Fahrenheit. The latest IPCC Intergovernmental Panel on Climate Change report urged we can't let it get to 2 degrees warming. We've got to stop it at 1.5 above pre-industrial levels to avoid severe damage to the world. 2% warming would be catastrophic to food production, water supplies, human health, as you're going to discuss in the next couple of days, coastal cities, energy production, national security, and economic prosperity. At the current rate of fossil fuel burning, we will reach the point of irreversibility between 2036 and 2046. Here's where we are right now, approximately. Here are the various scenarios by the supercomputer models. These are called the shared socioeconomic pathway scenarios, different scenarios here, okay? And obviously what we need to do is this one. But where we are, we're on this scenario right here, and with positive feedbacks that we don't know about yet, it could be up here. Okay, so where are we going to do? What are we going to do? All right, now, this is a fascinating graph. You know, I spent time at 10 years at CDC, and I remember this graph, like many others. This is the range of overwintering where it can survive the winter. The Aedes aegypti mosquito can survive the winter in the south here. Okay, that's the mosquito that brings Zika, yellow fever, dengue, and chikungunya. It's a bad actor. Okay, it can overwinter and cause outbreaks in the southern U.S. here. Okay, and same way it's in the world. It's in the earth. It's like this. Well, when Zika happened, CDC got reinterested in this issue and remapped this after I think about 40 years. This was really old, and they found Gulf. Look where it is now. It's all the way up into New England and Ohio and Kansas and Missouri and Northern California. Well above Dallas. See, Dallas and certainly Oklahoma was in the white. Now Oklahoma is in trouble. Now, why is that? Same thing over the world. This is expanded now, just from what it used to be. Well, it turns out when the climate warms, here's the northern Gulf Stream and the southern Gulf Stream, and in between is the equatorial zone or the tropical zone, where you got a lot of tropical diseases like diseases caused by Aedes aegypti. Okay. Well, when the Earth warms, the jet streams migrate poleward. And so you enlarge the equatorial zone, and this is evidence that the equatorial zone is enlarging. And we are now in the very northernmost part of the the tropical zone. Now, I mentioned the ice sheets. Okay, here they are. Now, how much will these increase sea level if they all melt? Well, of course, Arctic, if it melts, it won't increase sea level. But in Greenland, look, it has enough water to increase sea level if it all melts by 20 feet. We're talking right now about centimeters. This is 20 feet. Okay. The Western ice sheet has enough to increase global sea level by 10 feet. But the Eastern ice sheet, the Eastern Antarctic ice sheet, has enough to increase sea level by 190 feet. Think about that. This would inundate all the world's coastal cities where 80% of the world's people live. Okay, national security. Okay, most people don't realize this. The Arab Spring, remember the Arab Spring 2011, 2014, had a bunch of revolutions in the Middle East, throw off the dictators. They've been there forever, and it hadn't turned out well. You got more dictators back there mostly, but anyway, this was immediately preceded by a once-in-a-century winter crop failure in China that inflated global wheat prices. The top 9 wheat importing countries are in the Middle East. They get their wheat from China. So there were 7 of these countries had price protests involving people getting killed because the price, I remember when the prices were going up. And this ignited those revolutions. There were pent-up stresses, the dictatorships, poor management of the countries, but the spark that lit this was this wheat shortage. The Syrian civil war that we're paying for still now. This came out of the blue. Syria was immune to civil war, they thought, because it's a very educated country, very stable. It was preceded, this Syrian civil war, preceded by 4 years of the worst drought and crop failure in its history. Crop losses were 75%. Sheep herders lost 85% of their sheep. Hundreds of thousands of water wells were drilled, draining the aquifers. They ran dry. It caused a massive migration of rural populations to the cities that were not prepared for it. They couldn't manage them, and poor government management of the crisis caused then an eruption. Okay. And what happens in an eruption? It's not just demonstrations. What happens? Everything falls apart. People start starving. It grows insurgencies. You get extremists, dictators take over, and extremists come in and organize to have civil wars. Countries are already competing for control of the commercial passages and mineral rights in the melting Arctic. You can now drive a ship all the way across Canada, you know, in the quote Northwest Passage, which now exists. And the Russians and Chinese have already planted their flags on the bottom of the ocean there to start mining where it used to be just ice. Accelerating crop failures in Central America are stimulating northward immigration to the United States. Let me go into that. You remember the refugee caravans coming up from Mexico here? You remember that? Well, these weren't just refugees from Mexico. These were climate refugees, mainly from Central America, mainly from what's called the Golden Triangle, Guatemala, El Salvador, and Honduras. See here, this is the triangle, obviously. These had severe droughts leading up to this period, getting the worst at all in 2018, but really bad in 2015 and 16, driving these people up. 28% of all these asylum seekers were from Guatemala, El Salvador, and Honduras, only 7% from Mexico. 1.6 million of Central Americans living in here were suffering food insecurity from climate change. It's a UN survey. Half of these migrants left because, when they were interviewed, left because of lack of food. They were starving. Well, what happens? You get climate change, temperature fluctuations, shifting rain patterns, drought and crop failures. They've got a coffee rust going on now that's destroying a lot of their coffee crops. Hurricanes hitting them over and over again. Okay, this drives people either to migrate directly to North America or to more of them to their local cities, where they then crowd into the cities. There's no facilities and services to take care of them, no place to live. They don't have jobs. They spawn crime and exploitation, gangs arise, and so forth. And then that drives them up here. You hear a lot about the gangs down there driving the immigrants up, but people don't talk about, this hasn't been happening down there very long. This is new. And it's because climate change is now driving people up to here. And this is going to only intensify. Here's a report that comes out from the National Intelligence Council every several years, I think. This is the 2040, Global Trends 2040. It was March of 2021. A more contested world. The Defense Department and establishment is predicting more and more trouble in the world ahead. Climate change, environmental degradation are working together, eroding human security. Energy technologies can adapt, and adaptation can help, but basically instability and conflict is what's going to be caused. The world is going to erupt in worse and worse conflict. Think about what happened in the catastrophe after World War I, when the German population were all starving. What happened was Hitler. Okay, what happened in the Middle East after climate change disrupted it? ISIS and all those movements. This is what we're in for due to climate change. Okay, now, what I've been telling you up to now, this has been the good news, okay? What I'm going to tell you now is the bad news, and this is the dire effects of those feedback systems. What caused these big sudden jumps in CO2 concentration in the atmosphere from previously sequestered carbon dioxide and methane at the bottom of the ocean? It's thought now that the only thing that could have produced such a rapid increase was the setting off of some positive feedback cycles that would suddenly release a lot of between physical things and biological systems. And the biological systems will then create or liberate these gases and bubble them up into the atmosphere, out of the water into the atmosphere. Okay. The problem is, what's going to happen? Are we creating now with this thing? Are we creating vicious cycles? Well, ice and snow-covered surfaces reflect sunlight back into space, counteract global warming. Okay, the albedo effect. When land masses absorb light, so when the ice melts, exposes the land and the ocean, more light is absorbed, heating the earth and melting more ice. See, you got a positive feedback cycle. Vegetation, foresting, forests absorb and rain, jungles absorb, rainforests absorb CO2 and put it down into their roots and down into the ground in their roots. They sequester it underground. And you could sequester half of the carbon that we've released so far. You could sequester it if we could increase forests. But what happens when the forests are destroyed by drought, which is increasing, fires increasing, development, building out homes and cutting down the forests, deforestation, the roots decompose after the trees die and the grasses die, the roots decompose and release all that carbon, mostly as methane, 86 times the heat trapping ability of carbon dioxide. A vicious cycle. More warming, more fires, droughts, and development, more CO2 in the atmosphere and methane, more warming. Now here's the big one though. The Arctic tundra, up in the top layer of the Earth, the top zone of the Earth, up around the North Pole and in northern Siberia and northern Canada, that area has been frozen for hundreds of millions of years. It's been frozen. But before that, it was lush with green plants and later dinosaurs. And as those plants died over hundreds of millions of years, they piled up the dead plants but they froze eventually. And so you got up to a mile thick of this tundra. It's frozen. It had been frozen for millions of years. The problem is it's composed of plant and animal matter deposited and frozen there. It's up to a mile thick. Warming is 2 to 3 times higher in the Arctic than it is down here, remember? So thawed organic matter, as this thaws, this organic matter then will putrefy, releasing methane and CO2. This tundra, in fact, here's a picture of actually one of those areas melting. Looks like a big decubitus ulcer, doesn't it? And it gives you nightmares. It starts in the middle here, it thaws, and then as it thaws more, it grows outward in a big scar, a big ulcer, okay? And now the tundra all around the northern climes of the Earth, it contains 1,600 gigatons of CO2. So if that were to melt, it would release 1,600 gigatons, 1,600 trillion or 1.6 trillion tons. You remember what I told you? How much have we released since the Industrial Revolution by human means? 1,000. So this would more than double the amount of CO2 and methane that we've released already. As you can see, if this goes, it would be catastrophic. Here is a lake in Siberia. Pretty lake, isn't it? Well, this has been frozen tundra for millions of years, but has recently melted. And this is a lake. And you see these nice bubbles here, these little bubble islands? Those are bubbles of methane bubbling up from the putrefying plant matter that has now been exposed. This is happening. It's also happening in northern Canada. There are not many of these, but there are signs that this is starting to happen. And that is dire prediction. Now here is a fascinating study I really encourage you to read. Here's the reference by James Hansen, one of the most outstanding person working in this field. His team of really multidisciplinary scientists were studying this time to see what was the Earth like, what were the conditions on the Earth, how were they affected by this rapid increase in the CO2 concentration and increase in temperature of the Earth. just maybe predict some idea what's going to happen when this happens here on Earth in our time. Here's what here's one of the main, there were a number of findings, but the main finding that strikes me is that it's about this ocean current. There's a very important ocean current called the ocean conveyor belt, or the thermohaline circulation, or the AMOC, the Atlantic Meridional Overturning Circulation. I have to read this. I always have trouble pronouncing it. What happens is there's predominantly warm water here in the southern hemisphere, okay, around South America. That is pulled upward. It's warm, and it's got a small salt content basically, and it is pulled northern-wise by the heat gradient, the thermal gradient, and by the salinity gradient. That causes this water to flow rapidly, huge amounts of water on the surface flowing up northward. And as it goes up, it releases heat into the atmosphere, warms North America and Northern Europe with that heat that's coming out of it. And as it gets up here, it gets colder and colder, okay? And it gets more and more dense, gets more and more salty. And finally, when it gets up here, it gets very cold and very dense, and it dives down to the bottom. It's cooled by the Arctic and a very heavy salt content of the water up here. So it gets very heavy, and it dives down to the bottom, and then flows right back down at the bottom of the ocean. This going upward was on the top of the ocean, the surface. This goes down the bottom of the ocean, down to the bottom, and here, looking at the South Pole here it comes down, and it circulates around the South Pole, Antarctica, and keeps it cold, okay? Well, now what happens when the ice sheets, the Arctic ice sheet and the Greenland ice sheet, what happens when they melt? They dump a bunch of fresh water into the North Arctic Ocean up here, which dilutes the saline content, okay? And what this does, it slows the current. It reduces the salinity gradient, which then slows the velocity, and this slows down, and eventually, if this all melts, it eventually will stop it, and this will stop. And it's thought that the evidence indicates that that's what happened during the end of that ice age. This stopped. You then got a big ice age with ice over North America and Europe, okay? And then this slowed down, and the churning of the ocean from this thing stopped putting oxygen, mixing oxygen into the water. The aerobic metabolism stopped, and you got anaerobic metabolism. The plankton all died, and you produced less oxygen into the environment and produced more hydrogen sulfide, which is toxic to species. When the global temperature reached only slightly higher than today, large chunks of the polar ice disintegrated with a quick rise in sea level, 20 to 30 feet when that happened. It's generally agreed this will happen eventually, but gradually over centuries. That's what it's been thought. But this study suggested it will happen more abruptly because of that current stopping, and it will be over the next 50 years, not the next 200 years, destroying most of the world's larger cities and spoiling the atmosphere. Also, the change in those thermal gradients will produce huge pressure changes in the atmosphere, which will spawn storms greater than in ferocity than any storm that's ever been described in human history, because this hadn't happened in human history, okay? These storms will be much bigger than any hurricane we've ever seen. Here is geological evidence of that. This is a big boulder. Here's a little person here standing for reference. This boulder was thrown up by a violent storm back during this event, okay? Back at this time, it was violent storms threw this up on a 60-foot high cliff, okay? So showing you the ferocity of storms that what we've never seen before. So this will happen 50 years from now is what they're saying. Here is the number from 1980 to the present. This is the number of billion-dollar and more natural disasters in the United States. Okay, the number, this is by year. Each block is a year. Okay, Notice the increased rate of billion-dollar events. So we're starting to see the Earth get more unstable and more inhospitable climate. Now this is one of the most interesting graphs. This is 600 million years ago, and this is today. It's kind of backwards, but time is moving to the left. Here's the period of the dinosaurs. Here's the CO2 concentration in the atmosphere in thousands of parts per billion, per million, okay? And here's where we are now at about 416. Now, notice that every time there was a spike, what happened was there have been 5 mass extinction of species in the fossil record. They happened at a time when there were these increases in the CO2 concentration in the atmosphere. Now, there's a relentless decline in CO2, and that has to do with the tectonic plates moving and sequestering a lot of the CO2, the carbon underneath them, where it won't come out. But it's important to realize that the CO2 concentration had to get down to 500 parts per million before large mammals could start evolving. This is when large mammals started evolving at 500 parts per million. And human evolution, hominid evolution, was this period. Here was the glacial interglacial, this vast fluctuation occurred this long. The eastern ice sheet and the western ice sheets were formed. So our world was formed when it was below 500. What is it now? 416. What are we doing? So my conclusion, is the warming climate a serious threat to humans? Yes, global warming and climate change from human emissions of CO2 and greenhouse gases is no longer a debate within the scientific world. Don't let anybody tell you it is. It's not an issue of faith that you believe in or not. It's a rapidly growing threat to our children's future. It can be constrained by action in the next 11 years, but that's it. After that, the positive feedback cycles are going to get us. So that's why the urgency that scientists are saying.
Dr. Haley?
Yes.
Hi, we have 10 minutes remaining before our next presentation. I wanted to ask you if you'd like to continue with question 4 in your conclusions, or if you would
Let me just give a little bit here and we'll have 5 minutes for questions, okay?
Okay, that sounds
great.
It
ran over, but
you're doing amazing. Thank you.
I was too loquacious today. Okay. Should we invest in curtailing this? How can we do it? Okay, here's the job. We've got to stop this during this period of time. It's three simple things. You got to transition from fossil fuel burning to non-polluting renewables. Period. That slows the rate of warming, but it doesn't turn it back. You've got to remove CO2 from the atmosphere by negative emissions technology. This will slow and then reverse the warming. And if we stop methane and start sucking CO2 out of the atmosphere is what we have to do. This will actually reverse it and get us back to where we were. And then there's adaptation. See, this is mitigation, and then adaptation is kind of counter the most damaging effects. But this is like putting up seawalls and building more durable houses and stuff. But we don't want to waste all our money here. They're going to be tempting, but we got to do this first. Transitioning to fossil fuels, okay? Notice that most of the Earth's carbon that's unmined is in coal. This is why the fossil fuel industry wants coal. They'll never run out. Oil, gas are more limited. Okay, now this is in your handout, so I won't go into much detail. We've got to transition from coal and oil. Natural gas is the intermediate way, but we got to get rid of this soon. And here are the things that we're going to do. In your handout, so switch to renewable electricity. And there are lots of different alternatives that the current administration is already planning to address all of these, to pursue all of these. Put lots of federal money into bringing these online up to industrial strength quickly. We need to transition transportation to carbon-free. This can be done. It's already moving. New York Times had an article on Sunday saying that all the car manufacturers are suddenly falling over themselves to convert to electric. Okay, and finally, reduce energy wastage. You can read about these. Here's a great technology that Bill Gates helped fund. You can have nuclear reactors that don't melt down. And guess what they burn? They burn depleted nuclear fuel. Okay, you know, spent nuclear fuel that's been piling up, nuclear waste. Okay, anyway, sucking CO2 out of the atmosphere, it's already happening. There's a company called Climeworks and 3 or 4 other companies that already have working models. They just need to be scaled up. Technology improved. Okay, adaptation. Now, here is where we are going. Here's my final comment. When I saw this, here's what hit me. This is my generation. This is the lifespan of my generation. If I'm lucky, I'll live to be this long. Here's my children. That's you. This is how long you're going to live. Here's your children, my grandchildren. Your children, my grandchildren, are going to live to 2021 to see what we did to them. So every time I see my grandchildren, I think someday you're going to hate my generation. You may be living in caves if you're still alive, you know? Okay, so we didn't get to skepticism of denial, but it's all in the handout, so I better stop here. Okay, a couple of questions and then we'll move on to the next speaker.
Excellent. So we have a couple of questions that have come into the chat. One of these is, what can we do as individuals right now to help mitigate climate change?
That's the big question. I'm glad you asked that. Well, of course, I have 43 solar collectors on my roof. All right. I'm about to buy a Tesla automobile. Now I'm getting serious, but that's not going to do it. We all need to do those things, but that's not going to do anything. It's not going to solve the problem. The only way we can solve the problem, now listen to this, the only way we can solve this is marshal the power of the U.S. federal government to organize this, to fund the research, the scaling up that needs to be done, and use our foreign service, our diplomats, and our economic clout to get all the other countries in the world on board. And if the U.S. federal government isn't fully behind it and moving fast, it's not going to happen, and the worst is going to happen. So how can you do that? Well, we need to put people in elective office in the United States government and in state governments and local governments that are taking this seriously. This is the #1 issue for the world. And so you need to vote, you need to be organized, and it's your generation that's going to take the burden of this. So, you know, I went to college in the 60s, and we were all demonstrating on campuses and doing sit-ins and all of that stuff. I'm not even sure now why, but look, you guys have a real reason to do this. You've got to get organized, and you've got to get serious about it and force the country in that direction. So you've got to get elected the people who will do this. Right now, we have a team in there that are putting the best experts on it. The plan is solid. It will succeed. It will stop global warming if it continues, but you know, it's now stalled. It's not been voted in. It's stalled. And so you need to get busy and do something about this. And I'm not talking about party. It's not necessarily party. It's the problem here. It's the problem of people who take this seriously and want to save the world, and the people who don't. Okay, another question.
Another question is, how can fossil fuel-based economies like Oklahoma's pivot to renewable energy?
The same way, same answer. You got to get involved in your local government. You know, we've got midterm elections coming up. You've got to get Oklahoma electing people who won't deny this. You know, the fossil fuel companies down here in this part of the country are very active in trying to confuse people and elect people who will let their business survive longer. And what we need to do is get them to transition into renewables. And a lot of the big oil companies and coal companies they're buying up solar fields, and they are transitioning. But we need to do it more quickly, and that means incentives and the things that the current administration is doing will do that. And so you got to get busy at home.
We have a question. What are the implications for the cooling of the stratosphere? Will this impact humans, or is it changes in the troposphere that affects humans?
Yeah, it's changes in the troposphere that will affect humans. That is very important, though, because it is a major piece of evidence that proves what this is due to and is the foundation for why we should act.
We have another question. How does heat sink into the oceans if heat rises?
Very good question. Well, when you force enough heat down to the surface, it just sinks in, okay? So, yeah, heat rises, but when it gets so hot, the surface gets hotter too. And the hotter the surface is, the more heat's absorbed into the ocean. That's a very good question. I hadn't heard that one before.
Are there any other questions from the audience?
Yeah, anybody speak up if you want to.
Yes, please do.
Unmute and just blurt it out.
I wanted to know, okay, we have a question. How does pollution from lithium mining compare to fossil fuels?
Okay, yeah, that is there is some pollution from mining of anything, of course. That's not a game changer. That's not what's the problem with lithium is that it's a rare earth metal, and there's several rare cadmium and other rare earth metals that the Chinese have bought them all up now, and so they could be in the future in control of all of the battery technology. And that's not good for our country. We've been slow off the mark. Americans owned those rights and sold them to China a few years ago. And our government was asleep and didn't stop it. But the good news is, though, that there's our engineering community is coming up with replacements that with common elements will be able to replace those, and they already have working prototypes of batteries that don't require lithium and cadmium and these rare earth metals. So that will be solved pretty quickly, and China will be left holding some worthless assets, probably.
I think we have time for one question, one last question. Because the debate has been taken up by the larger culture divisions, what have been some convincing arguments to win over encamped skeptics?
That's a good question. There's actually literature on this, and I'm blocking on the sheet. A good friend of mine at Texas Tech is a scientist, and I've referenced her in my handout. Oh gosh, I can't call her name. Sorry, but anyway, and she's an evangelical Christian climate scientist who has written extensively.
Catherine Hayhoe?
Yeah, Catherine Hayhoe. Thank you very much. Sorry, I'm tired now. Catherine Hayhoe, Hayhoe, and just Google her on the internet and read some of the things she says. And she has a book out, just came out, and I have an autographed copy now. And it's a great book. She's from Texas Tech here, but she's head of some of the national commissions on climate change, very influential person, just very personable. She's an evangelical, her husband is an evangelical minister. They're vehement about climate change, that we need to protect it, and that the Bible doesn't tell us to do anything else. But she has this book where the whole book is about how do we talk to skeptics, and how do we convince them. And it's not by embarrassing them, and disparaging them. And just read her book. And I think that's the best thing I can say about that. And the other thing is read my handout. Learn this information so that you know why this is, and you know that it is true, and you can then basically hold your own in an argument, and you can feel confident in an argument that this is really true.
Dr. Haley, thank you so much for the enlightening information you shared with us. We have additional questions. I wonder if we could send those to you afterwards and have you type up some responses that we could send to our attendees afterwards.
You bet. Send it to everybody. That'd be great.